the figure that we've just constructed forms a triangle. The blue line, and then the upward green line, and then the diagonal across the solid. These three form a right triangle because we have a right angle here. Now the length of this side is the square root of 6 squared plus 3 squared, as we see here. The length of this side is 3. So now if we bring that triangle out into the open, or lay it down in the plane, it's going to be like so. And this is going to be the square root of 6 squared plus 3 squared. And this is going to be 3. So what's this going to be? It's going to be the square root of 6 squared plus 3 squared squared plus 3 squared, which is just equal, well, if we square the square root, we just get the 6 squared plus 3 squared. That's going to be the square root of 6 squared plus 3 squared plus 3 squared. Now this should convince you, and of course you can read your text and see it done in symbols and so forth, but this should convince you that the Pythagorean theorem extends into 3 dimensions. If we move 6 units, turn at a right angle, move 3 units, turn at a right angle to both of those directions and move another 3 units, then the displacement from our initial point to our final point will be the square root of 6 squared plus 3 squared plus 3 squared. In general, if we have a point, call it x sub 0, y sub 0, z sub 0, and a point x, y, z, and these points are visualized as being at the lower and upper corner. So if we have a vector that goes from this point to this point, then the sides of this rectangle are going to be x minus x naught, and our vector from here to here will be x minus x naught I plus y minus y naught j plus z minus z naught k, where k is a vector, a unit vector in the z direction. And the distance, the magnitude of this vector, if we call this vector, let's say a, then the magnitude of a, which is the length of that vector, is going to be the square root of x minus x naught squared plus y minus y naught squared plus z minus z naught squared.